So many of the retro consoles are very similar. They have a power regulator, they have batteries going into them or a DC plug that then lowers the voltage, and they power the system through usually a mechanical switch where the power actually passes through. So I'm going to explain to you exactly how the Game Boy Color handles this kind of power input through the power switch to this regulator out to the CPU, and how to diagnose and test your sort of power system of the Game Boy. It's a very common question I get asked on our Discord. If you want any more info on helping to repair consoles, anywhere from Ataris right the way up to PS5s, jump on the RetroSix Discord and we've got loads of people on there that can help and assist. But in this video, I'm just going to take you through the Game Boy Color specifically power system, which will include everything from putting the batteries in, the power flow of the entire battery into the system through the regulators to the screen, the CPU, and how to fully test that all works. This should be really useful for you guys to diagnose issues, and this should be usable on Game Boy Original, Game Boy Pocket, Game Boy Color, and even Game Boy Advance to some degree. Once you get to Game Boy Advance, there's a little bit more complicated design involved around the power regulation, so it's not quite the same, but the tips in this video are pretty much universally useful. So let's just jump in, strip this Game Boy Color down, and test the system. Okay, so on the back of this Game Boy Color, you'll have 6 tri-wing screws. These have already been unscrewed, and one was actually spinning, so I suspect this has been already undone. It might just be a no-fix donor board. You have then 2 more screws in the circuit board, which are Phillips head. You can remove those 2. And after this, the board is almost ready to come out. You just want to push the 2 little tabs on the ribbon connector gently, so they lift up. Get some tweezers and just lift the ribbon out. That's the screen ribbon. And then the board should come away freely. Oh, sorry, there's a 3rd screw there as well. Let's just get that one out. And then that comes out. Sometimes the speaker will stick to the shell if there's any kind of water damage or anything else. We can set all this aside for now. We don't really care about that part. So what we're interested in is diagnosing this kind of circuit. So there's 2 ways of looking at this. One, you can look at the main area of interest on a board, which would be, say, the CPU in this case, because the CPU needs to receive power to power up. And in order to do that, it needs a good ground and it needs a 5-volt supply. You could then backtrack, say, from the ground all the way to the source, which would be the ground of the battery, and from the 5-volt power all the way to wherever it should go, which would be through the power switch down to the regulator's 5-volt, and then through the regulator in essence that generates the voltage. Or you could go the opposite way, which most people do, which is to start at the power source, say the batteries, and track your way through the system. So let's just go ahead and show you how to generally figure this out. All this info I kind of give away, by the way, is on our RetroSix.wiki. So once I've done this video and I get time, I'll also be adding a document into the Game Boy Color page on the power system. I've already done one for the Game Boy Advance, for example, on how the power switch works. And you can see it's not just for retro consoles. I also have Switch, Series, and PS5 documentation as well. So this is always just being updated with useful documentation. So in order to get the schematics, if we just go to RetroSix.wiki and go to public files, this will take us to, let's remove that voltmeter a minute. This will take us to the public files that I share, and we have schematics and datasheets, Game Boy Color, and then we have the schematic here. So we can see we've got the schematic, and you don't need to worry too much about fully understanding schematics. You'll get used to it and what they do. But I'll just talk you through this quickly and fairly easily. We can see here is the battery. So we have the BT symbol. So we've got the negative, which is the left side, and the positive is the right side. So the left here is this negative spring, and the right is this positive spring. So we can see that the ground goes through, and this is the interesting part on the color, goes through the DC jack. And you see it goes into pin 3 and out of pin 2, and then through EM0, which is just an inductor for noise suppression, through another EM8 for more noise suppression. This one couples the noise between the power and the ground, so that's kind of a balanced coupling there, and that's a general noise filter. So we have EM8 and EM10, sorry, not EM0. So you can see even just the ground of the battery is quite a messy way until you get to the system ground, which is the symbol. The power goes out, and then ignoring the DC jack, it goes through EM6. It has what I'm presuming will be either a discharge or a voltage suppression diode here, D2, through a fuse, through the power switch, which when it's in the on position, flows in through pin 3, goes out through pin C, and then finally into the regulator, which the regulator's down here. Before we go further, let's just take a look at negative spring side. And you can see this is already quite corroded, but let's just ignore that for now. So this battery spring here goes firstly through pin 3 of the DC jack and should come out of pin 2. So the first place this goes is down to the DC jack here at pin 3. So what we want to check is, do we have good continuity, which means connection between here and pin 3? Because on the schematic, we should do. So if we want to test this system's working, we want to turn our meter to continuity mode. Check we get continuity. Yep, so we get continuity touching the leads. So now, from the battery spring, and I tend to try and do it from where the actual battery will make contact, so it's the most accurate result. So if I just put one probe there, you can see we have contact, but notice it's actually 12 ohms. So you see how it's like 10 to 12 ohms. That's not a good continuity. It should be 0. If we touch them together, you can see it should be 0 ohms. So even though we have continuity to pin 3, that's already too high of a resistance. 10 ohms is not good. And you can see it's probably due to all this damage. It's more than likely from here to the pad of the circuit here. So we could test that by just simply touching there to there. And you can see we've got 10 ohms. So from the spring's physical point here where the battery touches to simply get into the circuit board, we have 10 ohms. So let's see if the circuit's good, the trace between here and here, by touching the base there straight to the base here. And you can see that's good. So the issue here is we have a bad battery spring, quite clearly. So we would replace that. We have these on our store as well, so you can get all the spares and parts you need. But for testing, if we wanted to test this for now, we could just solder, say, a wire to here for ground and just ignore this battery spring. So we've proven that, one, the battery spring's got the high resistance. So just because it's beeping doesn't mean it's good. You can go to resistance mode if you don't want the beeps and test for resistance between things. And that will give you a reading every time. So the continuity, the beep you hear, will happen when it's less than 50 ohms. But that doesn't necessarily mean it's actually a good connection when it should be a direct connection. So just watch out for that. So we've gone from the battery spring to pin 3. Next, it should go over pin 3 and 2. So let's leave it in resistance mode for now. And you can see pin 2 to pin 3, which should be connected, is also completely disconnected. So there's no connection. So this has two problems already, because you can see clearly in the DC jack, pin 3 should go through, and this will be a spring inside the connector, and pin 2 becomes the ground of the system. So how would we fix this? One, we could actually go in here and try and fix. You can see there's battery acid here, this blue. So you can see there's damage on this connector already. But with the headphone jack, for example, inside the DC jack here, you'll have a spring similar to this spring here. So this is the headphone jack, but this is an example here where this is one pad, this metal contact here, and this spring inside here is another pad. And you can see it's meant to make contact like that. So when you put a headphone into your connector here, it pushes that plastic arm, which disconnects the two pins. When there's no headphone in, these should be connected, and that's how the amp for the audio turns off. Similarly, in the DC jack, when we insert the DC charger into this hole, it pushes on a spring inside of this connector, which is harder to see, which disconnects pin 2 and 3. So there'll be similar corrosion like this, meaning that pin 3 and 2 aren't making contact. So we have an option here to replace the spring for the spring. What option do we have for a bad DC jack? In order for it to work, we need to actually have continuity between pin 2 and 3, and at the minute it's basically no connection whatsoever. The first thing you can do is grab some IPA fluid, tip a load of IPA all in the connector, and with tweezers, I'm going to use one end of the tweezer and kind of just probe around lightly in there, just bearing in mind there's that center pinhole you don't want to be doing damage to. But what I'm trying to do is get the spring inside of here potentially moving, and it's unlikely we'll get this to connect this way. You'd normally need a new DC connector. So now let's just check out of curiosity if that helped at all. You can see it's come down to 200k from 1,000,000. So we've actually got 4 times better in theory, but this needs to be 0 ohms. So we could keep going. We can try our best to get this connector functioning. And let's see what that's done. And now we're down to 6 ohms. So you can actually see we've now got almost a working DC connector. Now the problem is, I wouldn't necessarily trust that this would last, because there's obviously corrosion inside those pins. See, it's kind of fluctuating already as the IPA dries. It's like 100 ohms, 90 ohms. It's changing all the time. And I bet if we left this for 10 minutes, that'd go back up high. So if you're not going to use the DC connector, and this is what I recommend when people are diagnosing problems on the board as well, I say bridge pin 2 and 3 on the DC jack. So all you're doing then is bypassing this DC jack's internal switch that disconnects the power from ground. And the point of this is when you insert a DC connector, that it disconnects the ground of the battery from the DC power. So the DC power doesn't try to charge non-chargeable batteries. That's the point of that disconnect. But if you're not going to use an old DC connector and your board doesn't currently work and you have no spares, just bridge pin 2 and 3. So on this particular board, I'm going to just bridge pin 2 and 3 because we will want to show this board working. And I guess a good thing here as well, I can quickly show that clearly based off that being so poor, we're very likely not going to have a working console here. We've got high resistance on the battery spring. We've got a DC jack that isn't passing power very well. So I'm not expecting much. But you can actually see it does power up, even though we've got those 2 issues. So this will be high resistance on the power switch. So this high resistance on the spring, we're kind of gripping a bit away from it, so it might be helping. But that 10 ohms are just to add to a bit of load. You just lose a bit of power. This, because we've cleaned it now, it will mean that we are getting power through the circuit, at least in some form, because we've cleaned it. Oh, I've actually made it now completely connected. So now it's had time to sit and soak in that IPA. It's actually gone better. That's why it's working. Whereas before, this probably wouldn't have worked. But either way, I wouldn't trust this DC connector, but it's working again, at least for the moment. But you know what to do if it fails or what to keep an eye out for there. So let's put this back into just continuity beep again for the moment. And let's see now. If we go from the battery spring to pin 3, it's first stop. In fact, no. Go back to resistance. It's annoying on the beep. So pin 3, we should get like the 10 ohms resistance, which we get roughly. It's gone a little bit better, sort of 4 ohms. Over there, you can see if I'm moving the battery spring, 70 ohms, 0 ohms. So it depends. This just moving this around is enough to make the connection. So I'll try and keep it still. And there you go, sort of a really up and downy 10 ohm to 1 ohm. So it's just not a consistent reading, but there we have 1 ohm. Jump over to the next step. You can see we've then got 3 ohms. So what we have so far is the battery negative goes through the DC jack just about. Now it should go through EM10 and through EM8 and go to ground. So if we look on the board, its next step as it comes out of pin 2 through this EM10 here, as you can see, through EM8 there, and this will be the ground pad. So I'm guessing this is the very first entry point into the system's ground here. So that EM8 is this EM8 here. So the path of current flows from here. It'll go down to pin 3, through a spring in here to pin 2, up to here, through here, and then the main system ground entry point goes here and connects to the rest of the board. So ultimately, we should have from the battery spring, we know we get to pin 2, so that's good. We should get to EM10 here, that's good. We should get to the other side, that's good. And we should get to the other side, which is ultimately system ground, which is okay. So we get sort of 8 ohms resistance from the battery to ground at the minute, due to obviously what we've seen, the corroded battery spring, the corroded DC jack, but it's good enough to currently power. So we can be assured at least the main system up to this point here has a good ground. So now let's just test a few extra ground points to make sure the ground is spreading throughout the system well. So you can see there's a good ground. There's a good ground. The main thing we want to check is, does the voltage regulator ground at the bottom have ground? And the other output ground have ground? Yep. And then leaving the pad on here for one side, go up to the CPU and check if the CPU has ground. And it does. So we've just proven one thing that most people leave out, and that's the ground side of the system. If you don't have ground, you might be testing here with your tester and probing, say, the input to the voltage regulator and measuring 5 volts or measuring 3 volts. But if this isn't ground, the regulator's not seen 5 volts. So by that I mean, say you put your testers in voltage mode, and you'd normally go, oh, let's find a ground point, here's a ground point, and let's test here for, say, 3 volts input. And you'd touch, and you'd be, oh yeah, we're getting 3 volts. However, this circuit, the actual regulator that needs to generate voltage, its ground is here, which is relative to this input. So you should be testing locally over the component like this, that you're getting the power. Otherwise, if this ground was broken, say through pin 2 and 3, this measurement would show correct, but this measurement would show incorrect. So it's important to firstly either check you have grounds where you expect them, so you can freely probe any ground and know it's the same measurement, or always test your kind of voltages local to the part of the system you're testing. Now that's the boring part out of the way, but that's the first important test. We've tested we have battery all the way through DC jack, through EM10, through EM8 and to ground. So next, how does the system receive power? So it comes out the positive spring. If we were caring about using the DC jack, the only thing left to check is the top of EM10. So this side of EM10 here, which is where the power flows. So it would come out of pin 1 of the DC jack, which is the center tap here. So the center pad with the bit there, that as power in from the DC jack, goes through this EM, goes through F2, and then through EM7. So you can see it goes out of here, through here, down through F2 here, and then through EM7, which you can see is here. So the trace goes up, through, and out. And then at this point here, it will now marry in with the battery spring positive. So we're not too concerned about the DC connector on this one, but just for completeness, you would test the input of the DC jack here to the actual center tap pin of the connector itself first to make sure power's getting through. And you can see there it is. So I have one tester probing the actual metal probe inside here, and the other testing the physical connection to the board. So we know when you plug the DC connector in, it should make its way to there. The next test would be from there through this EM filter to the top, just like the other one, which is good. And then you can go from here, say, through the fuse, F2, which is good. And finally through EM7 to here, which is good. And then you can go from EM7 in this case. This is where the 2 points should meet. And the DC jack should test continuity, if we've got this right, to the battery spring, and it does. So you can see that's the flow of power from the DC. It comes in, it goes through EM10, through F2, through EM7, and then up from EM7 to the battery spring. So that's the flow of power for the DC jack and the battery negative. So now we're more concerned about the battery's positive making its way to the power switch and then ultimately to the regulator. So for that, power flows from the battery spring through EM6. So let's start with that. And this is all just a multimeter in continuity mode and, well, resistance mode at the minute because we're looking for zero resistance, but same thing. So we want to go battery spring here and EM6 next, which is down here. So you can see EM6. If we touch on, and this is just an inductor, so it should go either side anyway. So there we go, we have connection there. Next it goes through F1. We'll come back to D2 in a moment, but it should go through F1, the main fuse. So it should go from this side, which it does, and output to this side, which it does. Now a note on fuses, even though they test well, they're very thin wire inside normally. So even though you're getting 0 ohms, it might be that the wire is really thin, and when you try to pass excessive current through, say 100 milliamps or so, this fuse is not allowing that much current through, and it either separates or simply limits the flow of current. So testing a fuse as 0 ohms or continuity isn't always guaranteed. If you have issues, it is sometimes worth just swapping these fuses out anyway. We sell resettable fuses, which means if you did short circuit or if they did blow, they electronically add really high resistance and prevent current from flowing, and then they cool down over the course of, say, 30 seconds and reconnect, and they reset themselves to a usable fuse. So we always replace our fuses with resettable fuses. But presuming it's got through the fuse, if this fuse was faulty, you'd have an open line. You'd have what it's saying now, OL, when you touched on. So if you touched on these and it was bad, definitely bad, this would say OL still. Now let's just touch on the D2. So you can technically remove D2 and the system would work. But what this will be doing, I'm pretty sure, is just a kind of like voltage suppressant or discharge, depending on how it's working, like reverse polarity protection or something like that. I haven't really looked into why this is, but my suspicion would be it would be a reverse polarity dump potentially. So if you put the DC jack in backwards, you imagine positive would flow effectively from positive, which is negative, and negative would be coming in here. So this would see that this ground here, which is connected to here in reverse, this would see potential of, say, 5 volts or 9 volts, and flow through the diode this way, back around, and probably just blow the fuse, to be honest. But it would allow reverse current to flow to potentially, I'd say, blow a fuse before going into the system as reverse voltage. But either way, that's not that important. The main thing is just to test this diode. So the only thing that can happen with this diode to negatively affect the system is if it was blown in a way that caused it to short. So a diode can blow two ways. It can blow apart and be disconnected, or it can fuse together and act like a dead short. If D2 fuses together and acts like a dead short, you simply have a short on your main power in to ground, which would just simply draw an infinite amount of current from whatever the batteries can provide, which can be a lot. So how do we test that the diode D2 here is working or not shorted? Well, the first way is if we go into actual continuity mode for touching, we go on a ground pad. So we touch on ground here. This side of the diode without the line should be ground, as you see on the schematic. The side without the line is ground, so that's right. The side away from the line, however, should not be ground, which it isn't. We're not going to beep. So we don't have a short through this diode to ground, that's one. We've also just tested that the main power to the system here, or the main battery power, isn't shorted to ground by doing that test. To test the diode, turn your meter to diode mode, and then the polarity of these matter. If we put it on with the wrong polarity, so black lead to the positive of the diode, which is here, the line on the diode means negative. So if we put this backwards, you should get an open circuit or nothing effectively, which we do. So this isn't allowing any voltage through that way, which is right. If we turn it the other way, the way the diode should work, we should get a voltage drop, which we do of 0.57, which is right for this diode. But the main test you won't concern yourself with really is, do you have a short, by checking for resistance to ground on the negative side of this diode. So this diode's good, that's all you need to be concerned about. So what comes next? So far we know if we apply power now to the battery springs, ground will be good, and power should flow all the way up to the outside of the fuse, and so far up to pin 3 of the power switch. So that means power now, where we're up to, is power comes out of F1 here, that's as far as we got in the circuit, and this F1 pad should go all the way up to pin 3 of the power switch, which is here. So how do we test that? We just get the testers again. I'm in resistance mode at the minute, so we're measuring resistance, not a beep. Go to pin 3 and go to F1. So this should be 0 ohms, and it is. So power now flows from here through a trace all the way up to the power switch, which is good. In the on position, there's just a little spring inside here, which I'll show you in a moment, which connects pin 3 through a spring like this to pin C. So it makes a connection between 3 and C. So we should get 0 ohms there, and we do. And if we slide the power switch over, it disconnects C and 3, and now there's just high resistance between the two. You slide the metal spring over again, and it joins them together. And then also, when you're sliding this power switch over this way, there's just a metal spring here. So by going into the off position, it joins pin 1, C, and 2 all together. So if we look at the schematic, pin 2 isn't connected, so it goes nowhere. Pin 3 and C, this is exactly how we're looking at it on the board right now. Pin 3 at the top is connected. When the spring inside here goes over, it connects the pin 3 to pin C, which goes into the voltage regulator, which is the next step. And when you turn the system off, so slide the spring into this orientation, it connects pin 1 and C. So what that does is connects the system voltage here that was originally providing power through pin 3. So C is common for the system voltage. This now, the system voltage, gets joined to pin 1, which goes to this R1 resistor, which simply gives a path for all the power in the system and all the capacitors to discharge through the power switch, through pin 1, and through the 750 ohm resistor. So this effectively discharges the capacitors in the system. And the point of that is, if you turn the console off and back on again quickly, these capacitors, for example, this one here, would store the charge when you disconnect power, and the system would stay powered on for a brief moment in time. But that means if you turned off and on fast, the system would be in an unstable state between a mid-range voltage not fully off and then going back on again. So to test the discharge resistor, you turn the switch to off, measure between C and 1, and you should see 0 ohms, which you do. So you know the power switch is correctly working in both positions. And now pin 1 should go from pin 1 and through this discharge resistor here that you see. So you should have a resistance of 750 ohms here, which you do, 735 ohms. So obviously it goes from pin 1 through to this side of the resistor, through the resistor itself, and then this side of the resistor, just as importantly, should be joined to ground. So we could pick the actual original ground point, which is important, and this resistor should be shorted to ground, which you can actually see it's far from shorted to ground at the minute. Let's try this ground over here, and that's a bit better. So you're getting sort of a bouncing bit of resistance. So you can see the ground, which we know it went up to here, okay. The ground from the top of the board to this battery spring we know is bad is not good. So you can see it's still important to check your grounds everywhere. So even though this resistor is good and the connection from here to here is good, the ground from here, which is what it needs to be, it needs to go to ground here in order to discharge the power, is not actually making its way back to the system power. So that is technically a problem that should be fixed. So if we see issues with that, we'll fix that. Let me just quickly show you this power switch, just so you know what it looks like inside. And you can see in here, there's the metal springs. So pin 3 is this pad and this pad. It's just dual pads. That's just a bit of plastic sitting over the top. But that's just one gold contact pad. Pin 2 is another that's not used. Pin C, the common, is this big pad. And pin 1 is this pad. And you can also see the way you clean the switches normally is gently scraping with tweezers to get rid of all the mess. And I'll do it one side so you can see the difference. And then a bit of IPA. Drip that in. Cotton wool bud. And rub in the pins. And you can see that's the difference between clean and unclean. And then on the spring itself, on the switch itself, if you turn over, you will see just a metal spring either side. So this is just a metal spring that is responsible for simply bridging. So if you imagine if it was in upside down, you can see this metal spring here would make contact with the copper pad under here and make contact with the other copper pad here, the C, there, and bridge them together through that piece of metal. So if you moved it to there, you can see if I position the switch in that position, it effectively joins this pad over to this pad. So it bridges them together, and then power flows through here, up and over, into C, and through to C. That's how the power switch is working. So let me just go ahead and quickly clean the other side of here. It'd be a shame not to. Place this switch back in. Fold this back over. So now we know the power switch is working. We know when we turn the switch in the on position, power flows from the positive down to EM6, through EM6, through F1, up through F1 to pin 3 to pin C through the power switch, and now C is the main place where the system receives power. So if you wanted to test your system and bypass all of these checks just to see if the console works, you could solder a wire to pin C and a wire to, say, this ground here, and apply 3 volts to C and ground to here, and that would bypass everything including the power switch, and you could see if your power LED turns on and the game runs. If that worked and putting batteries in didn't work, something we've just explained out of that whole process is damaged. However, once power comes from C, before it goes to the CPU, it actually gets regulated. So what happens after pin C? So pin C now goes down to capacitor 31 and into pin 1 of the regulator. So you can see we have here pin 1, pin 2, 3, 4, 5, 6 and 7. That regulator is all the way down here, and it's actually this on the back of the board here. This is the voltage regulator. You can see the pins labelled, pin 1 and then 3. So this is pin 1, 2 and 3, 4, 5, 6 and 7. Flip it over. So you have pin 1, 2, 3, 4, 5, 6, 7. So we should find that pin 3 here and pin 4 are ground. You see pin 3 and 4 are ground, which is right. Pin 2 is not connected, NC, so this pin here does nothing. So basically what we have is ground here, and the battery power from pin C of the power switch comes in here. So this is the input power to the regulator, that should be 3 volts. And then the output this side, this pin 7 is 5 volts. So this one's pin 7, and it should be 5 volts. These next two are LCD voltages for the LCD bias, which are 15 and 13 volts, I believe. M15 and 13.6. So I think one's negative, one's positive. I can't remember off the top of my head. But we can check that when we power this device up. But you should get 15 or minus 15 and 13.6 or minus 13.6, which we'll double check in a moment on these 2 pins. And then this pad's ground as well. So how do we check that? Well, at this point, we've kind of been done with continuity testing, other than the last step, which is, do you actually get continuity from pin C of the power switch down to the input, which is the next stage it goes, and you can see we do. So we get 0.1, which is as good as a direct connection. So we can be assured now that if we connect the ground of our bench power supply and the positive, which I've got 3 volts applied at the minute, to here, and let's see if, well, for one, it's no longer working by the looks of it. Yep, so you can see we're getting no power anymore. So my suspicion would be this obviously bad ground here. So how do we test that, I guess? We've got 3 volts applied here, so let's just test we do have 3 volts. And you can see we get 3 volts there. So let's test, like we said, with the ground connected to the battery spring, and go to the input of the regulator, and you can see it's showing 3 volts. But now if I take the ground probe off that ground and go to the local ground, as I mentioned, you can see we have no volts. So you'd think potentially the voltage regulator is working, because you test with your multimeter, say probed on ground, and then you probe over here and you go, oh, I can see 3 volts. But if we probe over here directly at local source, there is none. So it looks like we've lost ground from here to here again. So let's just test by putting the probe on the positive. Check we still have voltage here. We do, 3 volts. Check pin 3, which is the next stage. 3 volts, check pin 2, which I suspect is the problem, and there you go. So see how now pin 2 has failed? So now this DC connector has now failed again. So we cleaned it, it was working, and now power isn't passing between pin 3 and pin 2. So you know the solution I mentioned for that, which was for now, because we don't have a spare DC connector, and I haven't made the USB-C connector yet, which is coming very soon, I'm just going to bridge pin 2 and 3 on this DC connector. And the only caution here is just make sure not to plug in a DC connector and batteries at the same time if you're going to put this bridge over the 2. Otherwise, the DC connector, the DC plug that you got plugged in will attempt to charge non-rechargeable batteries, and that's not a good thing, and some can be dangerous and set fire. But this is a great way just to get your console up and running again while you're potentially ordering new parts, or you're going to replace it in future with a USB-C mod or something similar. So now we have that back on. I suspect now it will start working. And this is a really good board to kind of show this example because it is so corroded and bad. You can see exactly how you would diagnose issues with the knowledge we've just gained. So you can see now we have power light again when we turn on and off. So back to what we were meant to be testing anyway now, which was when we apply 3 volts into here, does the regulator work? So the first check, if you remember, is a local DC voltage over ground and input, and you can see now we're getting 3 volts in to this regulator board. So we can be assured the regulator directly through its ground and its power input is getting input power. And there's the 3 volts. So what's the next step? The next step is the output here. So if we go on the ground of the regulator, the top output should be 5 volts, which it is. The next one is negative 15 volts, as you see there, with the minus. The next one I think then is positive 13. Yeah, so you've got positive 13.6 and negative 15. So that regulator is fully working in the sense that at least we get the voltages. It doesn't mean it can provide the current required. That's another test, but overall, that would be a tested and working regulator now. So if we look at that now, it's kind of obvious this M15 will mean minus 15. That's what that M derivation will mean. So we've tested all the way, the power comes into the regulator, the power is also coming out of the regulator, and it goes off to VDD 15, which is going to the LCD, and VDD 13.6, which is also going to the LCD, which we don't care too much about there because you could test the system with just the power LED, which is provided by the 5 volts. But that shows a hopefully working regulator. After that, if this wasn't working, the only real thing we'd need to check if you didn't get red light is the 5 volts is going to where you'd expect. So C32 is the main capacitor here. So you could check that wasn't shorted to ground by disconnecting power first, because that can change the reading. Go into resistance mode or continuity, go into the system ground, checking first that ground is actually ground, so that should be 0 ohms, and it is, and checking the other side isn't 0 ohms, which it isn't. You can also do diode mode testing, which I've shown in the video how to do that. And you could put, say, the positive lead on ground, tap on the positive side, and you'll hear a short beep as it charges the capacitor and then disconnects. And that side should be a permanent beep indicating a short. So that's a good capacitor. After that, power comes down, goes into U7, which is a secondary regulator, which gives you a 3 volt system power. So we'd need to check that just the same. The ground pad 1 and 5 are okay. Pin 2 does connect to pin 7. Pin 1 and 5 are ground, and pin 3 does give you 3 volts output. So let's quickly take a look at that secondary stage power. And that U7 is right here. So just leaving it in diode mode for now. Going on the system ground point at the bottom here with the tester. We wanted to check 2 pins were grounded. So I don't know the pin out of this at the minute. But there's 1 grounded. There's 2 pins grounded. See the little white dot as well? That's indication of pin 1. So this pin 1 that is grounded will be right. And then we've got a second pin here grounded. And if we take a look, pin 1 and 5 should be grounded. So we can make the assumption then if we had to count, it would go pin 1, 2, 3, 4, 5. Pin 1 and 2 are grounded, so that's good. Pin 4 isn't connected, so we can ignore that top corner there, which probably won't go anywhere. And then pin 2 should connect to our regulator. So pin 2 will be this middle pin. So this middle pin here should connect all the way down to the output of our regulator, which it does. So that's where that's going. 5 volts is going out there, up to the middle pin. And finally the output then, which will be this pin here, should be 3 volts. So we just apply power back to the system again. We have the red light, so it's booted. Put the multimeter into voltage mode. Again, remember to test local voltages. So there's the local ground. And the output here should give us 3 volts. And you can see it gives us 3.3 volts. So that's a 3.3 volt regulator. So with all that tested, we've pretty much confirmed that the system has, in terms of power, good power input, good flow, the correct voltages. And we do know, however, we have a bad DC jack that needs replacing and a bad battery spring that needs replacing, both of which are actually on the ground side of the circuit, which is very easy for most people to miss. If there wasn't a visual clue here, you might not understand or notice that we have a really bad ground, and similar with this DC jack. There's no visible, real damage to kind of indicate that that's disconnecting power to the whole system. But hopefully this has been like a useful way for you to see how to kind of diagnose and test and follow the flow of power through the Game Boy Color system. It might seem a lot at first, we've covered a lot of steps, but what we've actually covered there is every single part of where the power flows. So you can take it from ground here, all the way through all the systems it needs to be to get to the ground here and the ground up here. And then you've taken the power, followed it through everywhere. We've taken the DC jack, followed that through and in. We've gone through the fuses, we've gone up to the second regulator and the first regulator, we've gone through the power switch. It's gone through pretty much the entire schematic there. So as well as understanding how to diagnose the Game Boy, hopefully this is a kind of good introduction into how to read schematics as well, and how to follow them and what to expect. If you enjoyed this kind of bit more deep dive into how something's working on the consoles, let me know and I'll happily do more sort of detailed explanations versus just test here to here, and if you don't have this, bridge this. Trying to explain the principles a little bit more, I think will help you guys self-diagnose in future and take this knowledge now and say apply it to a GPO or a GBP and kind of understand how similar they are and make the same assumptions using the schematics to diagnose yourself. But hopefully this will be useful for some of you guys that are struggling with Game Boy Colors and powers at the minute. And please do share these videos so that more people can discover the channel and this channel can grow nicely with more content. All your feedback's greatly appreciated as always, and I love to hear both the positive and the negative on anything to do with the channel or the products or the guides. If you need any more assistance or you need me to explain something better or you have any feedback, then definitely just let me know. And hopefully you guys can now repair a few more Game Boy Colors.